Hey, afternoon, everyone. Thank you for joining us today. We've got an amazing lineup, some greats of the geological world, Professor Richard Viljoen and Professor Bruce Cairncross. So we're delighted to have you here. Thank you so much for coming. So these talks came about, it's the last of the two series, 2 days of talks that we had, that Origin Centre has collaborated with the geosciences, and I'm the curator of Origin Centre, Dr. Tammy Hotchkiss Reynard, and we've been really happy to do this, and it all came about through the Geology Through a Lens exhibition. It's a temporary exhibition that's here at Origin Centre, and it's up till the end of September, so you still have some chance to come and see it. But it was all put together by a big group of Wits alumni, and of which Bruce and Richard were part of. And so we got them, and last week we had Dr. Ian Mackay and Dr. Bernard Zipfel also do talks. And so we're really happy that they were able to come and give some talks as part of Geotalks. So just to talk a little about the exhibition itself. So it's a wonderful photographic exhibition, and it is co-hosted by the Geological Museum Association and the Wits Faculty of Science and the Earth Sciences Cluster here at Wits. And it contains a range of amazing, rare and historically significant photographs that were taken by geoscientists and geologists over many years. We also have some displays of fossils and gems and mineral specimens on display here. And there's a huge range of high quality images from satellite images of Earth, beautiful geological landscapes, and then all the way down through to microscopic images. So I really encourage you to come and have a look at the exhibition while it's up. And so I'm going to first introduce our two speakers, and how it's going to work this afternoon is we'll have Prof. Viljoen will first give a talk, and then we'll have some time to ask questions in between. You can write any questions that you have in the chat or the Q&A, and then we'll pass over to Bruce to give his talk, about 20 to 30 minutes each talk. So, but you'll have your chance to ask your questions and have some discussion after each of the talks. So, okay, so let me introduce our wonderful speakers. So firstly, Professor Richard Viljoen obtained his degrees culminating in a PhD in geology in 1970 from the University of the Witwatersrand. During his PhD studies in Barberton, he, together with his twin brother Morris, were responsible for the discovery, description, and naming of an important new class of volcanic rock called komatiite. He spent 30 years in the mining industry and has more recently become involved in developing mining and geological heritage products in South Africa for the promotion of tourism and education. Richard is a recipient of a number of top local awards and international awards, and was president of the Geological Society of South Africa for 2 terms. Richard was appointed as an honorary professor at Wits in 1998. He has published over 60 scientific papers and was responsible for the publishing of 2 books, one on the great mineral fields of Africa and the other on Africa's top geological sites. Professor Bruce Cairncross obtained his MSc in coal sedimentology from the University of Natal, and after working for Rant Mines Limited Coal Division, joined the University of the Witwatersrand and obtained his PhD in 1986. He then joined Rand Afrikaans University Geology Department, where he served as head of department for 14 years, from 2003 to 2016. During which time at that time Rao merged with Wits Tech to form the University of Johannesburg, and he is currently Professor of Geology there. Bruce has written 11 books on Southern African minerals and gemstones and published over 150 articles on the same topics. He is an accomplished photographer and has won local and international awards for his mineral and gemstone photos. And a lot of them are actually in the exhibit here. So we have 2 amazing speakers today. So first, just before we pass over to Richard, Richard, you can put your camera on so long and share your screen. We just want to say it's an honor to have Richard here today. The talk is based on a field trip guide for the Geo Heritage tour of Johannesburg, which took place in 2016 as part of the 35 IGC, and of which his late brother Morris was the tour leader. And this talk that Richard is giving is presented in honor of Morris's memory. Cool. Over to you, Richard. Thank you so much.
Thanks, Tammy, for the introduction. Can everyone hear okay? Okay, good. Well, as Tammy has said, I'd like to give this talk in honor of my brother, Morris, who passed away recently, as you've heard. Also like to thank everyone for the messages of condolence that we have received and for inviting me to give this talk. As mentioned as well, this was part of the 35 IGC conference and field trips, and Morris led a trip through the Witwatersrand at that time, as well as two other field trips on Geo Heritage and mining geology during that conference. So this talk is based on that that field trip that he did through the Johannesburg area, which is being enlarged quite a bit. And he was working on that project, when he passed away. So I'd like to dedicate the talk to him. And if we have, let me just change the slides. Yeah, okay, so the first one, and this is something Morris was really interested and keen on, and that is the relationship between geology and topography. Here is the digital terrain image of the Witwatersrand area. To geologists, it's pretty self-explanatory, with the lower lying granitic area flanking the Witwatersrand plateau to the north. Northern suburbs of Johannesburg are based largely in this granitic terrain. And then the Witwatersrand plateau itself, which is essentially composed of the yellow rocks there, which are the Witwatersrand supergroup. So those are the important components. And of course, it's within the Witwatersrand supergroup that the gold-bearing reefs were first found. So highly important for the development of Johannesburg and for the development of South Africa. So if we look at and this forms the basis of the trip. The underlying geology has dictated all the activities in Johannesburg and the development of the city. You can see there the main components: the gold-bearing reefs of the Witwatersrand plateau outcropping disappearing under cover to the west, and the Johannesburg granite dome, which came up and up-domed and exposed the overlying largely sedimentary rocks. And the tour is shown here, a little bit more detail of the geology, starting off with a very prominent edge of the Witwatersrand plateau, which is essentially composed of Orange Grove quartzite in the yellow. He would start off in the greenstone material lying below Northcliffe Hill at Emma Park, where these komatiitic rocks that Tammy mentioned are exposed. So that is the starting point, the basement, and then into the Witwatersrand sediments, the quartzites, the Orange Grove quartzites, Linksfield Ridge, and the Northcliffe protuberance, and then progressing further past the contorted bed, which is a very important component of the story, as we'll hear, and then into the reefs of the upper Witwatersrand, which are the gold-bearing reefs, the main reef leader, and number. These are all stops on the tour, which show you you can actually see the main reef and main reef leader at the Standard Bank building, and then taking further, eventually looking at the Mondior conglomerates right at the top of the Witwatersrand, and then of course sort of mixing this in with the heritage of Johannesburg, the human heritage and the mining heritage of the city, and how everything sort of hinges back to these conglomerate reefs. So that's the theme of the tour, and we'll have a look at a couple of the stops. That's just a picture of the updoming. I think it's self-explanatory, with relatively flat-lying strata on figure A, and then figure B, the uplift of the dome, and the erosion exposing all the important rocks that we need. And in fact, without the updoming, we wouldn't have seen the gold-bearing reefs at all. So very, very important, the geology. And that is the North Cliff Ridge, one of the starting points, where you can see the southerly dipping Orange Grove quartzite, and then to the north, the lower lying undulated Johannesburg dome with the undulated, with the dendritic drainage patterns. From there, into indicating the position of the white quartzites of the Orange Grove, in this instance here, and the white water of the, this is in fact is the Witpoortjie Falls. So we believe, and many people do, there are different ideas, but that is the naming of the Witwatersrand. White water flowing over white rocks. Witwatersrand. And then going briefly into the discovery of gold. Gold was first discovered in the Crocodile and Yukskei rivers as alluvial gold panned by Pieter Jacob Marais in 1853. And these other gold fields all developed around the Kromdraai field, Blaubank, and then eventually the North Slope gold field by the Struben brothers. And that's quite an important one. All of these gold fields, I'm calling them now, they were small, but they were all based on quartz veins, the typical form of gold that all the prospectors knew about. They didn't, however, know about the gold in conglomerates, and it took a little while later for people to discover that the real bonanza lay in the conglomerate gold to the south. And that then became known as the South Slope Field, South Rand Slope Rand Gold Field. 1886 was the discovery of that reef by Harrison and Walker. So there is the first working at the North Slope Gold Field, the old Kloofendal area in the Confidence Reef mine of the Struben brothers, and their stamp battery. So one can see this typical quartz veining, which contains the gold, but obviously of smaller size compared to anything else. So the Strubens were very important here as the historical figures in the discovery of the Witwatersrand, because it was to this mill that Walker, who's working to further south, brought samples of conglomerate, which were crushed and found to contain payable gold. The Strubens had already crushed conglomerate, but the gold values were not payable. So that really was the most important historical site in a way. And there was the discovery of the Walker and Harrison, George Walker. And here you can see the working at Langlaagte, which is a historical site, blue plaque site, but unfortunately it's been pretty well destroyed now by Zamazamas and other activity in the area. That's how it did look. And basically the important reefs that are pointed out are the main reef below, which consists of a number of conglomerate bands in this area over here. And so the whole reef is mined over a few meters. And then the main reef leader, that was the real bonanza, containing extremely high values of gold and extending over some 40 kilometers. So that reef actually made the Witwatersrand, and it was mined continuously over that 40 kilometers. So that was the discovery site. And so that discovery site is visited if possible, but as I say, it's dilapidated and difficult to get to now. But the Johannesburg was laid out on this farm called Rantjieslaagte, sort of bordered on the north by the farm Bramfontein, and into the east by the farm Doornfontein, and the south Turfontein. So, and this shows the position of some of the early mines that occurred along the outcrop of the reef, starting off with the Ferreira Mine. And now it's the Ferreira stope that one visits on this tour, and you can see what was mined there in 1886, one of the first mining operations, as were all of these early mines over here. And that is the museum, if you like, at the center. This is the main reef leader. You can see the bands of conglomerates, similar to what you saw at Langlaagte, but less well developed. And then, of course, this slot over here is where the main reef leader has been taken out. And then this is the early shot of Johannesburg with Ferreira, Ignatius Ferreira, who was the guy who was in charge of the whole development of the gold field in the early days. But then the problem arose with the mines becoming deeper, and it was more difficult to mine these narrow reefs from surface, so one had to go underground. And this is the time when labor had to start importing labor, both from Southern Africa and from the Chinese, in fact, and they didn't last for too long, however. So as we got deeper, it was important it cost money. And so the people who really got the thing going were these chaps here, the landlords, and they, in fact, started the whole gold mining business. And the system of the mining houses, Cecil Rhodes and Charles Rudd, formed gold fields in 1887. And this character here, Barney Bonato, started JCI soon after. There's the one of the old JCI building, which is now a heritage site in Johannesburg, and there's the new JCI building. Obviously made a lot of money. So that's the story of JCI. I don't think it exists any longer, but as a company, it's been broken up. And then, of course, the Rand mines formed by Eckstein and Phillips, Lionel Phillips, and the beginning of the group system, as I mentioned. But then the whole system hit a problem, and that was that the free milling gold that had been found near surface, where the pyrite in the conglomerate was oxidized, became very difficult, and no more free milling, because as you get deeper in the unoxidized material below 30 meters, one required another technique to separate it, and that also cost money. However, we were pretty lucky in that in the late 1880s, MacArthur and Forrest had discovered the or worked with the cyanide process of liberation of gold from the unoxidized conglomerate. So that was a major hurdle, and people thought that that was the end of the gold fields, and they left Johannesburg in hordes. But it was this guy here, and Robinson, Sir Benjamin Robinson, who actually started off at his mine with a chlorination plant. Now, chlorination plants had been used in the Bendigo, Ballarat, and other gold fields around the world very successfully. But this process of chlorination didn't really work in the Witwatersrand. And so people then realized that the answer was to use the chlorination process. And he introduced the first cyanide vats at the Robinson Deep gold mine. Now, these guys, the landlords, made a lot of money, and they were tired of living in the dirt and grime of the mining area to the south. So they all moved up to the north and built their houses on the Parktown Ridge, the Orange Grove quartzsite. And many of the houses there were built of the Orange Grove quartzsite, very, very distinctive. And they were designed largely by Herbert Baker. And it was called Baker Village, in fact. So the tour actually goes past a few of these houses and shows you who's who in the mining world. There was Baker and his house, the stone house, still in existence. There was the Northwoods and John Dale Lace and his wife, who was a real socialite in Johannesburg. She drove a carriage drawn by a zebra. So that is Northwoods, and then the Phillips, Sir Lionel and his wife, Lady Florence, and they built this house over here, which is still in existence as the firstly as a Jewish orphanage, but later taken over by the Hollard insurance officers. And she, in fact, was a patron of the arts and established the Johannesburg Art Gallery. The problem was, as mentioned, labor was required to work on these mines, and the obvious source was locally from Southern Africa, but they tried, as I indicated earlier, the demonstration with the Chinese. That didn't work out. This is just an historical photograph showing some of the mine workers arriving and showing a place called Baobab Hill. In the period 1919 to 27, these black workers were recruited, and this is one of their stopping spots, which is a heritage site at the moment. And then the mine laborers were housed in what are called compounds. And this compound system was the basis of all sorts of problems that have arisen lately, but essentially they were single-sex compounds and interesting kind of activities going on. Anyhow, the next thing was that education was required for all the children of the people who were flocking into Johannesburg, and a number of schools are built. Incidentally, we'll come back and show you later that we visit a compound at the Newtown precinct. There is a nicely preserved compound, and you can see exactly how the mine workers live. From the educational point of view, the schools are also built pretty close to the Parktown Ridge. Rodine, the girls' school, King Edward's, St. John's, also part of it, Banato Park and Parktown High, and then, of course, the University of the Rant, which developed from the South African School of Mines and became a university in 1922, and hence the centennial year of the founding of Wits University. Now, Wits University played a very, very important part, as did the schools, but at Wits, many of the mining engineers that were required, the geologists, the metallurgists, the geophysicists, plus a range of other disciplines, electrical engineers, etc., mechanical engineers, they were all, or many of them, were trained at Wits. So this whole educational thing became a very, very important aspect of the development. The other school that I should have mentioned is Jeppe High, which is also one of the schools that was founded fairly early on. And there are some of the schools, Banato Park, it's now been demolished, Rodine, St. John's, and Wits University, which everyone knows pretty well. So then these guys started making a lot of money after all these problems had been sorted out and they'd built their houses, etc. This here is a collection of photographs showing between the chains, which is where many of the deals were done at the stock exchange, which was developed. And that became a famous place between the chains, Simmons Street, between Market and Commissioner. So in order to get things moving, there was a trio of people who came up with a brilliant idea. And that was how do we trace these gold-bearing reefs? And three people, Leopold Reinecker from Goldfields, Kramen, also Goldfields, and then Carlton Jones, who was a mining engineer, also Goldfields, came up with the idea that if they could follow the magnetic signature of these certain beds within the lower Witwatersrand sequence, one could trace these magnetic beds below cover rocks to the west of Randfontein and use that as a proxy for finding out where the gold-bearing reefs should occur. And this they did, and this incidentally is the contorted bed, which is one of the important magnetic markers. And you can see the main components here: chert and jasper, iron oxide minerals, hematite and magnetite. And it outcrops actually just outside Wits University in Jan Smuts Avenue and also at Melly Street. And this is one of the stops on the tour to show you this very, very important outcrop. And this is the blueprint that emerged for the finding of the West Wits goldfield. The orange color is where the rocks outcrop. The black and the dotted lines are the magnetic markers that were traced to the west, and the red is the position of the main reef group, and the gray is the position of the options taken out by Goldfields, and they established one of the biggest gold fields in the world. And at the same time, mines were really getting deep now, not the a couple of 100 meters, but below 2 kilometers. And that also needed money. And this money was provided by people like Ernest Oppenheimer, who developed the Western Deeps Levels mine below 2,280 meters here, and other mines in the Witwatersrand goldfield. And with this discovery of the West Wits, other goldfields started opening up, the Free State goldfield and the Evander goldfield later. So the whole thing started moving, but most of these new goldfields were undercover, not in the exposed Witwatersrand plateau, but undercover. And that needed money. And that's why the mining house system was so important. And that is the extent now of the Witwatersrand basin as we know it, all starting from Ferreira Stope over here, where the reefs outcrop, and reefs outcrop here shown in blue, and then they occur in here is the West Wits line, the Western Deeps over here. These are future deep resources, in fact. The Clarksdorp goldfield, the Free State goldfield, and the Evander goldfield. And we estimate that there are still something like 35,000 to 40,000 tons of gold remaining in the Witwatersrand. But it is deep, and to mine that very deep gold, we'll need robotics, we'll need a new approach, and we'll need money. But one day it'll probably be mined, but that's how the whole Witwatersrand developed. And that story is told in this trip, this tour that Morris led. And with deep mining comes other problems, these problems being rock mechanic problems, rock failure, pressure bursts, and all sorts of methods have been introduced by rock engineers, again, many trained at Wits, to support the workings at depth. Otherwise, you get these catastrophic rock failures. And not only rock failures, every aspect of mining has been researched at the Chamber of Mines research laboratories, and they are world leaders in research into mining, and particularly deep level mining. Wits again has played a very important role in the training of people in this field. And then finally, towards the end, people started retreating some of the dumps, which were not well done in the earlier days, extracting gold and leaving, unfortunately, a lot of waste in the form of unoxidized pyrite, which became oxidized to form what's called efflorescence. And this material then ran off as acid mine drainage. And that is a total no-no, totally toxic material. However, all of these problems have been very well sorted out by the environmentalists. And this has become a major topic of research and development in the Witwatersrand mines at the moment. So that's with the dying of a gold field, these are the problems that have to be overcome. And the tour ends off with conglomerates right at the top of the Witwatersrand Plateau sequence called the Mondior or Ellsberg conglomerates. And they are overlain, you can see them, they're still dipping to the south, overlain by these rocks here with a lot of very good vegetation. Those are the lavas, the Ventersdorp lavas, which cap the Witwatersrand and which give rise to very fertile soil and hence the vegetation pattern that you see. Here on the Witwatersrand material, which is very silicious, not very nutritious, you get typical sugar bush vegetation. So they're nice contrast. The other thing you see here is the house of Petrus Johannes Meyer, who many feel that name, he gave the name to Johannesburg, one of the early farmers and pioneers in Johannesburg. And that is his house, which can be seen today at just below the Klippriviersberg mountains. And finally, leaving us with the present day Johannesburg. And that really is the story of the tour and how geology and well-trained mining engineers and geologists have played a huge part in the development of the city of Johannesburg. So thank you very much. And if there are any questions, we can discuss them.
Thank you so much. That was fascinating. It's amazing how some things that we see every day, when you're not coming from a geological perspective, you just don't notice these things. So it was fascinating. Thank you. We have 2 questions already. If the audience does want to type in other questions, please do. We've got a question from Charles Day. What effect did the Frederford Dome meteor events have on the Witwatersrand geology?
Yeah, I just need to unmute myself here, I think.
We can hear you. It's fine.
Oh, can you hear me? Oh, good.
Yeah, we can hear you.
Yes, a good question. And there is another section which I didn't put in to show that there was uplift by the Frederford Dome had a similar effect to the Johannesburg Dome, but it was caused by the meteorite, most people believe, and the meteorite elastic rebound caused the updoming. In the case of the Johannesburg Dome, the updoming was caused by tectonic events in the Earth's crust. So it was an interaction eventually between the Frederford updome and the Johannesburg updome, that the Witwatersrand was exposed. And in fact, Witwatersrand strata are exposed around the rim of Frederford, and there was a gold field there which was established also in the early I think it was about 1888 or somewhere around there, and mined for a little while, but the values are low compared to the values of the reefs outcropping south of Johannesburg. So yeah, it had a very, very important, excuse the pun, impact. Frederford Dome.
Cool, thanks. Then another question also from Charles. Please, can you comment on the geology of the Suikerbos Rant Nature Reserve? It seems to consist of both indigenous and sedimentary formations. Or igneous.
Oh, igneous, yeah, igneous and sedimentary, yeah. Yeah, I mean, there are, I believe that the Vennersdorp lava is exposed in that area, which is a igneous rock. And I think there may be some Karoo dolerite intrusions, which are igneous rock. But essentially, it is composed of Witwatersrand strata, in which you can see conglomerates and quartzites, etc. And I think there's some shales there as well. So yeah, there are other rock types which are the Vennersdorp lava, as I mentioned, overlies the Witwatersrand in most places. Okay.
Well, then another question for Mark. How far west and east is the Orange Grove quartzite feature exposed?
Okay, it's exposed, well exposed north of Krugersdorp, and it's well exposed in the area to the west of Randfontein, and finally disappears below that dolomite in the area to about between Randfontein and Western area. To the east, it's exposed right the way through to Benoni, close to the Kempton Park and the airport, that area, but then it gets covered by younger Karoo strata. So it's over a considerable strike distance, probably, I don't know, maybe 100 kilometers it's exposed. But then sadly, everything becomes covered by younger formations.
Then a question from Lou Ashwell. Can you comment on the Witwatersrand diamonds?
Sorry, the Witwatersrand?
Diamonds.
Diamonds, yes. That's very interesting that the Witwatersrand does contain these diamonds. They are quite unusual in that they are greenish in color, and we think that this is due to radioactive radiation that has caused the green color. The origin of those diamonds must have been from some pre-Witwatersrand kimberlite, or maybe it wasn't kimberlite in those days. Maybe there was another mechanism for getting diamonds to the surface. And that's a good area of research to find out exactly what's happening. So one needs to look at the associated minerals in the heavy minerals in the Witwatersrand, of which there are a huge number, including garnets, including chromite, including ilmenite, which is now being changed to leucoxene, plus a number of other important minerals. So I think we need to look at the diamonds in combination with these other minerals, which could give us a clue as to the origin of those diamonds, whether it was in the form of a true kimberlite as we know it now, or some other magma that reached the surface carrying diamonds. Perhaps komatiite. And these were eroded, of course, and then deposited as alluvial deposits in the Karoo conglomerates.
Oh, I didn't even know about Witwatersrand diamonds, so now I'm learning. I think these tours are wonderful, and I'm so disappointed that I haven't been on one before, and I hope that maybe this is a conversation that can happen with geosciences as well, as a way of honoring your brother and yourself, that you can carry on with these kind of tours in some way.
Yeah, and I don't know if I mentioned earlier, he already is working on a whole number of these booklets and tours, including a book on the geology of Kruger Park and the Barberton area, which is also now a World Heritage Site, plus the Garden Route, where he's just written a booklet, which I'm busy wanting to complete on his behalf. So he had a lot of things in the pipeline, and they're huge potential for developing our mining and geoheritage sites, no doubt.
Oh, sure. We have one last question. We have a comment from James Allen saying, thank you so much for the talk and for your dedication to Morris. And then from Mark, we've got to almost stop the questions. We'll have last 2 questions and then we'll move on to Bruce's talk. But from Mark, he asks, were the early alluvial findings in the Yixka and Crocodile rivers the result of erosion of the uplift? Is there any sense of the age of this sort of erosion event?
Yeah, I think, yeah, that alluvial gold, it certainly doesn't seem as though it was from the Witwatersrand conglomerates. There's no evidence of that at all, but it's probably from the gold-bearing quartz veins that you saw in the various quartz vein gold mines sort of rimming the dome, like the Strubens quartz reef that I showed you. Erosion of that material and concentration is one of the things. But there might also have been gold in the greenstone belts themselves. And we're looking at this question now as to what the origin of the gold in the Witwatersrand is. And that's a very important question. And what we're looking at is the occurrence of masses of ultramafic rock immediately north, just below the Witwatersrand. There may have been something in these rocks. We believe they may have been enriched in gold, in fact. But that's a big story, and it's at this stage, let's say that gold came from the quartz vein type of gold in the gold fields that surround the dome, not necessarily from the conglomerates, funnily enough.
Thank you so much, Richard. So I think we should move on to Bruce's talk. So Bruce, you can share your screen and turn on your video. Okay, cool. You can take it away.
Okay, thanks, Tammy, for that introduction. And thanks, Richard, for your talk. It was extremely interesting. I'd like to preface my talk just with 3 slides, as we are sitting in September, which is Heritage Month. And just to talk a little bit about Geo Heritage. And I think in most circles, if one thinks of Geo Heritage, and like this journal, there's actually a Geo Heritage journal now published by Springer. It deals almost exclusively with things like geosites, geo trails, and geoparks. And there is another arm or leg to Geo Heritage, and that's what is called portable Geo Heritage. And
sorry, Bruce, just want to say we can't see your screen at the moment. I'm not sure if you...
sorry.
Yeah.
Let's
try share again.
Sorry, I just need to end my show. I thought you could see it. I don't know why I can't see the Zoom screen anymore.
Yeah. It's always what happens. Works perfectly in the trial run, and then when you go live, it doesn't. I
can actually see your the minimized screen of yourself, but I can't see the full Zoom.
Maybe just double click on it and then see if it works.
Bruce, can you see the green share screen button at the bottom of your Zoom screen?
Yeah, I see it now. That's my apologies. Okay.
Just take you straight to your share window. There we go.
Perfect.
Okay. Okay. We're good to go.
Good to go. Thanks, Bruce.
Okay. Sorry, as I was saying, I've got three slides just before my talk, just to talk about Geo Heritage. And I was saying that with portable Geo Heritage, the name itself explains the things that can be actually carried, and it's, for example, rocks and fossils and minerals, it's actually something which isn't often considered within the Geo Heritage portfolio, but there is, in fact, the Heritage Act, the SARA Act, the National Heritage Resources Act of 1999, that serves to protect all items of heritage in South Africa, and interestingly, including portable geoheritage objects such as fossils and meteorites. These are protected by this Act, and also, according to the Act, rare geological specimens. So in effect, rare geological specimens are protected by law by this Act. And but one needs to ask the question, how useful or in fact relevant is this protection? And if one looks at where do you go to see these portable geoheritage items, obviously the museums in South Africa, where you go to see displays of rocks and minerals and fossils and also meteorites. But in fact, in my opinion, it doesn't really serve the need. And I've actually questioned this in a publication of some time ago. And does the Heritage Act actually protect our geoheritage resources, and in particular what they have in their legislation as rare geological specimens? Because in fact, there's no definition of these in the Act or anywhere. And I just thought about it and came up with about 12 or 13 definitions of rarity. And so if we are talking about these mineral specimens, the museums, unfortunately, that are controlled by the municipalities, the town councils, and by the governments, are unfortunately under-resourced and ill-equipped. So in fact, most, and by no means are all geological specimens rare by any means. So not all are protected by law. And in fact, that's what leads to one of the very large hobbies, in fact, globally, which is collecting minerals. And I think it's true to say that most of the mineral specimens in South Africa that are of any sort of meaning are perhaps in private hands, with a few exceptions. So my talk today about the Messina copper mines is really about this portable geoheritage. I'd like to highlight some of the specimens that have come out of these mines over their 80+ year of their existence. And maybe just also to mention that this talk, as you heard, is part of the Geology Through a Lens series, and it ties in with the exhibition, as you heard from Tammy, in the Origins Center at Wits, and it is a collaborative effort. The idea of the photographic exhibition was in fact conceived by the Geological Museum Association. That is the voluntary committee that serves the downtown Johannesburg Geology Museum. And I would also like to acknowledge the role that Maurice Viljoen has played on that committee, because the committee consists of Professor Jill Drennan, who chairs the committee, myself, then also Richard and Maurice for many years, and then Catherine James Kleinans, the curator. So both of the Viljoen brothers have really done a great deal to serve the GMA committee. And in fact, some of Maurice's photos are also on show at this exhibit. So if you have the chance to go there to see it, I would highly, I would highly suggest it. So the Messina Copper Mining District, where is it located? Well, it's the Messina mines are virtually almost on the border in the Limpopo province, the border with Zimbabwe. And maybe just to note that the town now is called Musina, M-U-S-I-N-A, but the mines, even though they have closed, are still Messina, which is the old spelling, because obviously the mines were registered legal entities and their name remains the same, and it hasn't changed since the new political the dispensation that we have in South Africa. So what I'd like to do is just briefly go over the discovery and the history and the geology of the mines, then show you some of these minerals, the portable geoheritage, and then actually what has been going on there in the years 2000s, because although the mines closed in '92, there's been some activity, and especially at the Arten Villa mine. So that's basically the outline of my talk. So here's a view up there taken in the field of the Messina mine just before it closed, a typical view if you've been up into that Limpopo area with the mine dumps in the background, and on the right-hand side, some of you can see the old headgear, and some of the chimneys of the copper smelter. So a very typical geographic scene up there with the baobab trees. In the summer, very hot and dry. Now, the history of the Messina mines goes back for millennia. And in fact, I've just got a photograph here of a sheet of basically native copper that came from the mine, and this old label is actually stuck on there in 1950. So it's one of the older specimens. But in fact, the history goes back a lot further than that, to pre-European times. And there is clear evidence up there from outcrop and from archaeological artifacts that the local indigenous Africans were working copper in this region long before the advent of the Europeans. There are artifacts, there are tools, and in fact, there's even in the historical records of the early travelers, there's evidence that the early Portuguese explorers were trading for copper artifacts already in the 15th century. It could be argued that maybe if they were at the coast at Mozambique and they were trading these copper beads and whatever artifacts, they may not have been from Messina, they could have been from Palabora, for example. But there's definitely evidence of these early African workings. And as you can see here in this old photo of this report by Trevor, it's a bit old and grainy, but just in the red circle here is the early Messina headgear. But in the foreground is one of the African excavations on the outcrop where they obviously found the showing of the copper, the blue and the green staining on the rock. And they then would actually exploit this down to the water level, where they then got into the sulfide ore and they couldn't do anything with it. And they were using this to extract their copper. And it's documented that every one of the modern headgears, the European headgears, was either sited on or near an earlier Africa excavation. If we're looking at the European history, the Messina mine history really starts in the early 1900s, just after the Boer War, where a certain Lieutenant Colonel Grenfell went with an expedition up north to explore, to look for copper. And some of the people in his party, named Harper and Digby and Campbell, in fact, are the names which some of the later shafts were named after. So the Campbell shaft, Digby, Harper shafts were named after some of the party in Grenfell's in his expedition. So in 1905, the Messina Development Company was found and European modern mining began. And here's a photograph of Grenfell. This was hanging in the Messina main office when I was up there in the early 1990s. There was a lot of interesting historical photographs. I don't know what happened to them. But here he is with his dog and his Martini Henry, and typical, with a pith helmet and a pipe in his mouth. And here also are the old shafts. This is the original number 4 shaft. These would certainly be Geo Heritage items, so to speak, not portable, but of historical importance. And then the number 5 shaft that finally closed in 92. So if we look at these mines, this is a Google Earth image. So north is to the top right. Here's the Limpopo River. Here's the town of Messina. From northeast to southwest, the Artenville mine, the Spence mine, the Messina, the number 5 shaft, and you can see the relics of the mining operation here. Then the Harper, and then the Campbell shaft. So they're more or less in a line. And one wonders why. And well, you need to actually wonder no further if one has a look at the geology. Because if you look at a simplified geological map of the area, this is the Limpopo belt. Again, there is the Messina mine, so the town of Messina. So there's Artenville going across to the Campbell mine. Essentially, the rocks here are granite. They're high-grade metamorphic rocks, granite, gneisses, and metaquartzites. But what is important is the Messina fault, which is this line which is coming along here, and the Dow-Tokwe fault. And the black blobs that one sees here are the various ore bodies, and they are all located close to or virtually on the fault line of the Messina fault. So undoubtedly, in work done by Jacobson, for example, at Wits University, and by Terence McCarthy, this structure had to have played a role in the mineralization, and it's felt that perhaps the ore-forming fluids moved along the fault plane as a pathway at the time. And that accounts for the linear, for the orientation. Now, the shape of the ore bodies, this was out of the article by Barneman in the 1986 Mineral Resources Deposit. They are like upside down turnips or carrots, as you can see here. This is the Messina mine with the shaft going down to about 1,200 meters. You see there's the fault, which is cross-cutting through these lodes or through the ore bodies that had various names. And Jacobson's work at the Art and Villa mine mapped these in 3 dimensions. And they are actually zoned. They are like sheaths of alteration zones as one goes into the ore body, from hydrothermal alteration on the outside to these breccias of or rather the fragmented rock on the inside. So the rocks themselves are zoned, and the mineralization, the copper minerals, occur inside the breccia. But the sulfides themselves are actually zoned. Here's a slice at right angles through one of the ore bodies, and you can see going from the outside in, you pass through essentially a chalcopyrite zone, then into bornite, and then in the cores, the richest of the copper minerals, the chalcocite zones. So they are zoned according to the lithology and also largely according to the sulfide minerals. And in fact, even on a smaller scale, here's a quartz crystal that's been sawn down the middle and polished, and even the quartz crystals themselves are zoned. You can see this sequential growth as this quartz crystal grew from the fluid, growing upwards, leaving what's called the phantoms inside the quartz, and just actually trapped inside here are some of the chalcopyrite crystals, the crystals that must have still been around in the fluid at the time of formation of these quartz crystals. So the mineralization is very simple. It's virtually only copper, chalcopyrite, bornite, and chalcocite. There is virtually no lead or zinc or any other minerals. And it's associated with a lot of albertization, cerussitization, and alteration that's been going on. And as I said, the ore bodies are commonly zoned. Here's a slide taken by Terence McCarthy, published in an honors project at Wits University, Lang, saying a notable feature through the breccia bodies is the development of vugs, those are cavities or hollows, in the rock, lined with well-formed crystals of quartz and calcite. So these are the mineral specimens that are highly desired by collectors, in fact, all around the world. The Messina mine specimens, quartz specimens, are in fact world famous with museums and with private collectors. So in early 1992, Roger Dixon and I were fortunate to go underground in the mine just before it closed, and when we were doing the fieldwork for our book. And here's some slides I took at the time. It was an interesting experience, a bit like going into Dante's Inferno. It was 100% humidity, over 45 degrees. And yeah, it was an interesting experience. As you can see, the infrastructure was not that great. So let's look at some of these minerals now, or the portable Geo Heritage. You know, one could ask, what's the point of these? Well, they are collected by amateurs and by professionals. They are collected as aesthetic items. They are collected for research purposes, for various reasons, as for many things that are collected. And in fact, the mineral collecting hobby is a multi-billion-dollar hobby worldwide. So this is a calcite specimen. It's about 5-6 odd centimeters. This, interestingly enough, these orange crystals are albite, which is a plagioclase feldspar, which is normally a creamy off-white color. But these are an orangey color, and Jacobson in his PhD determined that they have a high iron content, which is causing this color to occur in what would be otherwise a relatively neutral white or creamy colored albite. And it's on a doubly terminated quartz crystal. This is a barite specimen, barium sulfate, from the Messina No. 5 shaft. And barite was actually rare, but it forms these flat bladed crystals. This is the calcite crystal in the Johannesburg Geological Museum. It's 28 centimeters. It's about the size of a rugby ball. And some of these calcites were actually quite large. This is a doubly terminated specimen in, as I say, the museum collection downtown. This is also calcite. It's a close-up view of a specimen, 3.4 centimeters, and all of these are scalenohedral or so-called dog's tooth calcites, but they've all got inclusions of these cloudy blue spots inside. And these are some of the secondary copper silicate minerals that I'm going to show you a little bit later, but which are normally included in quartz, but in this case, they are in these calcite crystals. And it's these blue copper minerals that have made the mine specimens so famous. Here's a sheet of pure native copper, which was also found underground in the mines in places, pure copper. And here's a specimen of chalcopyrite, typical for the mineral, this brassy color, and one of the main copper species. And then chalcocite, the copper sulfide, again, 2 euhedral specimens, quite small, but showing this typical outline of these steel gray crystals. In most of these things for mineral collecting, as with any hobby, whether it's stamps or minerals or carpets, perfection is always desired. So if there's any damage in the specimen, it tends to detract from the value. That's from a collectible standpoint, but it does not detract whatsoever from any scientific importance. Here's a hematite crystal, iron. There's a lot of hematitization, actually, and a lot of iron hematite is associated with the quartz crystals. And then epidote is very common. Epidotization is one of the alteration processes there. And here you see green epidote crystals, pistachio green, scattered over this 11 centimeter quartz specimen. All of these would have been coming out of these cavities in the breccia ore bodies. And here, close up, it's only 7 millimeters, but these tabular orange crystals were thought to be piemontite. And in fact, more recent work has actually shown them to be epidote also, but they have a high content of manganese, giving them this orangey red color as opposed to the normal green. So these are manganese-rich epidote from the number 5 shaft. Okay, so let's look at these blue copper silicates, which have rather esoteric names: ahowite, papagoite, and shatterkite. Now, first of all, some of the quartz specimens from Messina are enormous. Here is one in a garden. It measures about 2 by 2 meters, and you can get a sense of the scale of it if you look at the tree ferns round about, which are quite large. Now, one can ask, how did that leave the mine? That's a good question. It must have come out in some sort of a skip or something. Huge. But what made the Messina specimens really famous when they first hit the market in more or less the mid-1980s was this blue mineral included inside the quartz specimens. And it's a mineral called ahowite, A-J-O-I-T-E. It was actually discovered originally in Pima County in Arizona at the Aho mine. And there's an article in the Mineralogical Record that actually describes these. But these inclusions have made what is normally just a colorless quartz highly collectible, and especially, and in particular, with the esoteric community, the people who actually collect minerals of all sorts for various, not just aesthetic, but spiritual or healing purposes. So there's a huge market there for especially these Messina specimens. So here's 2 showing this blue ahowite, and there you can see the composition. It's basically an alkali copper aluminium silicate. It's a secondary mineral that, again, as the quartz was crystallizing, so these elements were in the liquid and they got trapped inside the quartz, giving these beautiful blue components to normally the tops of the crystals. This is the second one, which is called papagoite. And again, it's a calcium copper aluminium silicate. And these are 4 crystals. The one at the back is about 7 centimeters. It's a darker blue mineral. And again, interestingly enough, the type locality, papagoite, was discovered also in Arizona. And it was named after, at that time, the indigenous American Indians who lived in that area. However, the name, the Papagoa, was actually given to those people by the American colonialists, and they subsequently denounced it. And they have given themselves a more indigenous name, but the name of the mineral actually persists. Here's another one, a small specimen of showing this blue inclusion inside the Papagoa, I beg your pardon, inside the quartz crystal. Now, there was some question about these minerals, because if you've got a blue mineral inside a quartz crystal and you want to properly identify it, you essentially would have to crush the quartz to liberate the blue to be able to identify it. And for a long time, it was thought to be that these blue minerals were ahawite and also papagoite and the other one, which is the shattuckite. So a couple of years ago, I had an honor student who did a project, and we sacrificed a few of the specimens in my collection and did some polished sections, and we did Raman XRD and some SEM EDS work, and showed quite clearly that the dark blue that you see here and here is indeed papagoite. So it's actually confirmed. And as far as I can see, it's perhaps for the first time that it's been quantitatively done. Here's a fantastic, almost like fireworks, top of a quartz crystal that's been polished to show this variety of inclusions in these Messina quartzes. There's the blue there's the papagoite, there's red hematite. Here are streams of tiny threads of native copper. There's clay, there's kaolinite, forming a complete, as I say, almost like a fireworks display inside. It's been polished to show these internal, the internal minerals, because quite often the Messina quartz specimens are coated with a secondary coating and you can't see what's inside. As you see here, this is a specimen that three of us were up at Messina in the 1980s, and a miner had some specimens there he was wanting to sell. And he had these in a box that he didn't even sell. He said, you can have these are rubbish. And I could just see there was a bit of blue showing here under this heavily oxidized coating. So not this piece, but three others I took and I polished, and this is what came out inside. So the reverse side of these is what I showed you in the previous slide, but you can see there is hematite, red hematite. There are these phantoms, so-called phantoms, showing the sequential growth of white kaolin. There's the blue, that's the ahawite, and the dark blue here is the papagoite. So really quite spectacular inclusions in these quartz specimens. Just before perhaps going away from this, just to mention another one of the copper minerals, which is called cuprorevite. Now, this is a calcium copper silicate, and you'll notice compared to the others, it's got no aluminium. And for many, many years, it was known as a synthetic compound called Egyptian blue. And this goes back to eons, to the time even of the Egyptians who used Egyptian blue. They would make it synthetically and use it to color a lot of their artifacts and, in fact, their sarcophagi, Egyptian blue. And recently, with a colleague, Mike Rumsey, who's the curator of the Natural History Museum in London, we've just written a paper on what has been shown to be cuprorevite from the Messina mine that they have in their collection at the Natural History Museum in London. And it was a very interesting exercise and detective story to trace these down and to find out how they came there. And that all goes back to a certain geologist, Edgar Mountain, who was head of the geology department at Rhodes University. But that's for another talk. So the mine's closed in '92. What has happened since then? Well, some enterprising individuals discovered some outcrop at the old Art and Villa mine. And just to remind you where it is, over here in the east. And they saw some quartz crystals outcropping and started to dig some holes, which became larger holes. And they then collected in the Art and Villa diggings second generation of specimens after the mines had officially closed. And these created a frenzy in the collecting market when they came out, because up till then, the Messina specimens were virtually gone because the mines had closed. So just to show you a few slides of these to end up. This is some quartz from those diggings with hematite inside. This is a quartz specimen that was for sale at the international show in Munich in 2008 that I saw a dealer selling, and I just quickly took a picture. This is from Art and Villa. And then these, again, which are quite stunning, they are doubly terminated quartz, again, with the same assemblage of hematite, light blue ahawite, and the dark blue papagoite from the Art and Villa diggings. Here's one which looks quite bizarre. It's again it's doubly terminated, and it's got inclusions of epidite, papagoite, hematite, and kaolinite. And this has not been polished. This is a natural crystal. There's another one showing these vermiform or worm-like threads penetrating through the quartz crystal of hematite, and again with the clay, the kaolin, and the arowite. And finally, just to show you one of the largest of these that came from that Artenville digging. This is a specimen. It was 1.3 meters long. It weighed 400 kilograms, and it's a bit hard to get a feel of the size of it in this picture that I took in the garage of the owner. But he had a few pictures that he gave to me, and so yeah, you can see here's the size of the specimen. It's absolutely enormous. It's been professionally cleaned. He took it to the Denver show several years ago and attempted to sell it, and he was hoping it would go to a museum, but it didn't sell. So subsequently, it was actually broken up into a number of individual smaller specimens, and in that way, I think the bulk of them have been sold. So without further ado, thank you for your attention, and I hope you found that interesting. Thanks.
Oh, thank you, Bruce. An interesting ending with a picture of Ronnie Mackenzie. I went to his house a few years ago and we were doing a show on meteorites, and it's just this whole museum, and I would have been upset if I hadn't seen this amazing this huge crystal or series of crystals. But anyway, but I wanted to, there's a question from Charles. So also I'd encourage the audience just to write some questions if you have. But from Charles, how long would you say a 7-centimeter quartz crystal would take to form?
Well, that's a good question, and I would answer it with how long is a piece of string? Interestingly enough, it's always been thought that the larger the crystal, the longer it takes to form. But there's been some work in recent times which has suggested, now this isn't true for every large crystal, but that some crystals may actually form and grow very rapidly, actually in a matter of not even 100 years. So there's a number of factors that come into play. It's the temperature of the fluid that whatever the mineral is, in this case quartz, that it is crystallizing from. It's the pressure regime. But yeah, the answer is it's not easy to know, but some recent research tends to indicate, if you take as an example, if you look at the growth of synthetic quartz crystals, which are grown in autoclaves, then they grow these for pure silica and they use them for the manufacture of silicon chips. They can grow a synthetic quartz crystal of, I'm just looking at my ruler, of about 25 centimeters in 6 weeks in an autoclave. Now that's actually simulating, if you like, that's under extreme high pressure. But there's a large crystal growing artificially, and perhaps if the same conditions are met deep down in the Earth's crust, it could be equally rapid. So, yeah.
We've got 2 hands up. Grant, are they able to chat? I see that Sianda has typed out a question. He says, are we able to commercialize the Guahlati recent discovery of quartz crystals, assist maybe in determining the value?
Just ask, is the Guahlati the quartz crystals that were found at Ladysmith that they thought were diamonds?
As far as I know, yeah.
Is it those?
Is that right, Sianda? Is that those ones you're meaning?
Okay, well, if it is those,
Yes.
okay, well, unfortunately, quartz is one of the most common of minerals on Earth, and to a lot of collectors, quartz crystals are not even worthy of collecting, unfortunately, because they're so common. So one can buy an ordinary quartz crystal the size of my thumb, maybe for 5 Rand or so. So selling them, in my opinion, wouldn't be a really viable thing unless they are fairly large. And the most important thing, they have to be absolutely undamaged. If they have the slightest chip on the edge of the crystal, or on especially the top, they are valueless. So they'd have to be collected extremely carefully so that they're not damaged, and that's not easy. But I personally think they may not have a high value because, as I say, there's a lot of quartz around. Look, when you start getting inclusions inside them of other minerals, their value increases. But I think if I could suggest, maybe the way to do it would be to look for some dealers in minerals in South Africa, and there are some on the internet. You just need to Google them. they could have some value. I see that Lou's actually said, for example, as Herkimer diamonds. Well, that is a possibility. Herkimer diamonds are actually quartz crystals that were mined and are still mined or dug out by people in New York State in America. And they are quartz crystals, but they look like diamonds, hence their name, Herkimer diamonds, because one of the original people who discovered them thought they were diamonds, and he went and he pegged the whole area for a large amount of money, and then they turned out to be quartz. But those are brilliant, shiny, water clear, doubly terminated, and extremely aesthetic. They even used in their natural state in jewelry. Now, if those sort of Herkimer diamonds, so-called, came from this deposit, and again, they were undamaged, they could have some value. And I do know there are some other localities in KwaZulu-Natal, for example, at Moy River, where they find similar type of quartz that are approaching what one would call Herkimer diamonds. So I would say there is potential, but collecting them undamaged is critical.
Okay, we've got a question from Sharad. He's going to ask his question live. Thanks, Grant. Cool, go ahead.
Hi, Bruce. Thanks for a great talk. You haven't mentioned anything about the origin of the Messina mineralization. Any thoughts about that?
Okay, well, I've actually got an hour talk, but I culled it down to 20 minutes, I think. Well, you know, when Roger Dixon and I did our book, we had a bit of a dilemma because we thought, should we put this into the Archean chapter because it's sitting in the Limpopo belt, or should we put it in the Phanerozoic, because just north of the Limpopo is the Nuanetsi complex that, if memory serves me right, is sort of Karoo age, I think. I hope I'm right, but it's definitely younger than the Limpopo belt. And I know there is one school of thought that thinks that the intrusion of that complex, which is quite nearby, other side of the river, may have had some role in introducing the mineralizing fluids. But Sharad, apart from that, I haven't read too much of late, I'll be honest, regarding the genesis of those particular deposits. I mean, I don't know if you have any thoughts on that. I know it's fair to pass the question to you.
Well, I think Jacobson already had demonstrated that the alteration that is associated with the mineralization actually affects dikes which he dated as Karoo age dikes. So it's clear already from Jacobson's work in the 70s that the Messina mineralization is probably of Karoo age or post-Karoo.
Yeah, I think that was the generally accepted theory, actually, if, now that I recall.
Well, we've got a few more questions coming through from Mark. What preserves the thin threads that appear in some of the crystals shown? Just the nature of chemistry.
The thin threads, their morphology.
Hematite. Yeah, I'm not sure if it's maybe the hematite threads that.
Yeah, look, I don't know. I suppose it's just the way that mineral is then crystallizing in the fluid at the time. It is nucleating along as a thread, you know, as opposed to a distinct crystal or as a very fine, almost cloudy mass. I can't really answer that, but it's obviously due to the nature of the crystallization at the time of each of those minerals as to their morphology that they have inside the quartz crystals. I see Sue's asked a question about geophysics.
Oh, you can just say the question as well.
Yeah. Is there potential to use geophysics to find more areas to mine for mineral samples? Is the market large enough in the Limpopo? I presume by geophysics, you mean to look for further copper deposits. I suppose there is potential for that, and especially, you know, seeing that the original mines were all located on previous older workings. I would say probably there is potential. The market for these Messina included quartz crystals is open-ended. You just got to look on any of the websites of people who are selling these, and the prices are outrageously high. They can demand US dollar prices in the thousands of dollars. So if one could use some sort of geophysical, whether ground penetrating radar or something, to find more pockets, and again excavate them economically, commercially, without damage. There is definitely a market for the quartz crystals, and obviously for larger copper deposits.
Okay, let's see if there's some other ones coming through. I think most have been answered. Close my screen now with the Q&A. Let me have a look. Are you aware of any exploration activity for copper in the area around Messina currently?
I'm not personally aware. Maybe someone else does know of, but I haven't been up there for a long time, I'll be honest. But I'm not aware of any renewed exploration.
Okay. And I think last one from Isabel. What were the average depths of the copper deposits mined in the Messina complex?
Yeah, well, that Messina number 5 shaft went down to over 1,000 meters, up to 1,200 meters. When we were there underground, we went to about, if I remember correctly, about 600 to 700 meters below surface. And the fact that it's in the Limpopo belt, where the crust of the earth is relatively thin compared to if you're on a craton, the heat flow is much higher. And as I said, it is extremely hot and humid down there. So they were quite deep mines.
Okay, great. I think that's Sianda. Do you still have a question? I see your hand still up. I'll allow you to talk if you do have a question still, or follow up.
Yeah, thanks. No, I just wanted to make a comment. I think for me, this talk was actually extremely educational, especially when you introduced the subjects that there is some pre-colonial history that is related to geoscientific discoveries, because I think quite often that is not taught. You hear it in the streets. And of course, that could, like what you have demonstrated, that they use the same pits to actually mine next to these pits. And I think that is a very, for me, critical indigenous knowledge that should be incorporated in this geoscience curriculum. And of course, that for me fits into decolonization of knowledge. It is not necessarily changing knowledge, but telling it from the lenses of everyone who participates in that knowledge production. So thank you very much. I think that's very critical, a piece of history, and I think we should do more so that education also is much more reflective and inclusive. Thank you.
Now, thanks for your comment. I appreciate that, and I can only reinforce what you're saying. I gave a talk last week in another forum on the O'Keefe copper deposits. You know, and those, if you read the history of those, they were discovered in 1685, by Simon van der Stel, the governor of the Cape at the time. But you read about that long before he or any of his community went up there to, at that time, the Namaqualand. There was already copper being exploited again by the indigenous Africans. And that is the story of many copper gold deposits in not just South Africa, but in Southern Africa. If you just go up north into Namibia, into the Otavi mountain land, there are those huge lead zinc deposits at Tsumeb, Grootfontein, Combat. They were all being mined and exploited in outcrop for hundreds of years before the Europeans arrived. And so I can only concur with what you were saying.
And there's another hand up, Anne. I'll give you the permission to talk. There we go. You can just unmute yourself. You still want to ask a question?
Yes, please. It's actually Anne's husband, Chris. Bruce, good evening to you. Fabulous talk. Have you been associated with any of the copper deposits found in Botswana, Matsatama, near the Sewer Spit, and such like?
No, not at all. I'm unfamiliar with those.
Because when I worked for what was then the Rhodesian Selection Trust, one bright spark geologist said, guys, we've not found one outcrop that the ancients didn't get before us. So let's fly a grid over this area in stereo and look for these workings. Well, they did that. They got so carried away with themselves, they didn't fly a baseline in. And as an impoverished student, I was given a chain gang to go and work out where the heck these pictures were, because he said, go out and find these things. And they said, well, boss, we actually don't know where to start because there's no baseline. So it was really used as a method of exploration, which was, I think, probably the first off. But they were so good. There was not one piece of evidence that we had found something that they didn't. So they picked up the outcrops 100%.
Yeah, no, look, that's true. And in fact, even if you go to Palabora, exactly the same at Palabora as well. Same thing there.
And the only evidence that we have of, the people that were there were trading beads, but the actual evidence of copper being extracted must have been regarded as gold and very precious. One tiny little twist, which maybe is part of a bangle or something, was the only thing that I could find on what were apparently their living sites, where you get a white color on the photograph, and it's a chalk extract of some kind or other. Now, whether they made bricks or something out of it, I don't know, but nothing grows there very well. So you see them on these aerial photographs.
Thanks.
So great evidence of these earlier people.
Indeed.
Oh, thanks. Okay, so we've had a whole nice host of questions. I hope we've got through everybody's questions, also for Richard as well. So just before we say goodbye, I just would like to, so this is the last talk that we'll be doing with Origin Centre as part of the Geology Through a Lens exhibition. But once again, I encourage you to come and have a look. You've got one more month till the end of September. And on the 24th of September, on Heritage Day, we're hoping to have an open day or an activity day where you can bring your kids and invite your families to come, and we'll have a whole lot of activities, COVID-friendly activities and social distancing. And we hope that you can bring your kids to come and enjoy that as well. And then also the next Geotalks happening next week is by Leo Vonopatis from Wits. And it is titled Indicator Minerals of Granitic Mineralization. So same time, same place next week. And thank you so much. And again, to Prof. Richard Viljoen and Prof. Bruce Cancross, thank you very much for your talks. They were very interesting, and we had a wonderful audience today. So thank you so much.
No, thank you, Tammy. Thanks for hosting. Thank you.
Cool, thank you.